welcome back. We are in week 11 of inverse methods in heat transfer. In the last video, I gave you a preliminary explanation of what pins are. And within that, I had just told you about how the loss function for the ODE can be used as a ODE or the PDE, even though I didn't talk about PDEs there, can be used as a substitute of having ground truth. In this video, I would like to give you a simpler explanation that doesn't exist within the literature, but I would like to give you a simple explanation and a sort of intuitive explanation for how pins came about. Okay, and once you understand this video well enough, I think you will be able to see the last video also in a better light and also the upcoming videos within this week clearly. Okay, so let's go back to a simple problem or even a slightly complicated problem. So let's take a 2D problem. And let's say we are solving del square t del x square equal to 0, which means del square t del x square plus del square t del y square equal to 0. We know that the solution, given certain boundary conditions, is given by some t of xy. This is the solution. So we know this already. Unfortunately, we can't find it analytically. Okay, so the problem, of course, is no analytical solution. If you were doing CFD, the way to solve using CFD would be exactly what I told you before. Split this into some mesh, treat each one of these as an independent unknown, each one of these points as an independent unknown, and then turn this into difference equation, approximate it, and then solve it. We are going to take a slightly different approach now. Okay, so what I call the slightly more intuitive or a simpler approach, which will directly lead to pins once we use neural networks. Okay. So what I'm going to do is I'm going to assume, and this should remind you of the forward models that we did. We are going to assume some solution t of xy, which is approximate. Okay, remember, it's not exact. To t of xy. So in this sense, this is our hypothesis. Okay. Now, not only that, I am going to give, as I would ask you to recollect what I had talked about earlier in machine learning, I am going to give a form that this approximation takes. Except now I'm going to take a very simple form. Last time I took a neural network, we can't write or make head or tail of what it is doing. But here, I'm going to assume t of xy equal to a plus bx plus cx square plus dy plus ey square plus, let's say, fxy. Now, instead of that, having a, b, c, d, I'm going to write w0 plus w1x plus w2x square plus w3y plus w4y square plus w5xy. Okay. Now, this is a function. This is obviously a function. Now, the number of unknowns here are 6 unknowns. We have w0 through w5, which are not known, which would mean we need 6 equations to solve them. Okay. Now, if you need 6 equations to solve them, there are several ways of doing so. One method could have been you actually have an experiment and you make, let's say, 6 measurements. So let's call these points 1, 2, 3, 4, 5, 6. To solve for w0 through w5. So remember, the moment you solve for w0 through w5, you know the temperature at every point here because I have written temperature as an expression. Okay. So if I solve for w0 through w5, you can use method 1, which is give 6 measurements of temperatures. So the moment I give 6 measurements for temperatures, what happens? I'll have 6 equations. How so? For example, let us say that at this point, let's say this was location x1, y1, the temperature was measured to be T1 either through some prior simulation or through an experiment, you know this. So you will say that at x1, y1, temperature was T1. So this will say W0 plus W1 x1 plus W2 x1 square plus W3 y1 plus W4 y1 square plus W5 x1 y1 equal to T1. Okay. You can write equations such as this. In general, you'll have W0 plus W1 xi, so on and so forth, up till W5 xi by I equal to Ti. If you write this as a matrix, the unknowns, remember, are W0, W1, W2, W3, W4, W5. On the right-hand side, you will have T1 through T6. And here you will have x1, x1 square, y1, y1 square. Sorry, there will be a constant term, which is 1. Then x1, x1 square, y1, y1 square, and then x1, y1. Similarly, 1, x2, x2 square, so on and so forth, up till x2, y2. So you have 6 equations, 6 unknowns. Solve. And there you have your temperatures. Okay, so sorry, there you have W0 through W5. But suppose I don't have these. I don't have T1, T2, T3, T4, T5, T6. Now this would be comparable to usual NN solutions or the surrogate method. Okay. I'll explain the connection later on, but this is similar to the surrogate solution. But there's an alternate method. So let me call this the second method. Let's give a name to method 1, which is through temperature measurement. Now let's look at method 2. Method 2 says impose the PDE. Okay. Now, even though I don't know the temperature at this point, I do have one piece of information. What is that? I know this. I know that del square T del x square plus del square T del y square is equal to 0 at these points. What does that lead to? Okay. Impose the PDE. How do I impose the PDE? I already know the temperature expression. W0 plus etc. up till W5 xy. Then I can find out what del square T del x square is. Now, del square T del x square, let's write this out just for our reference. Del square T del x square will have 2 W2. This term, and all the other terms actually go to 0. Okay. So W0, W1, simply differentiate the expression for T and you get this expression. What about del square T del y square? Del square T del y square will give you 2 W4. So we now get the equation that W2 plus W4 equal to 0. Now, unfortunately, for the function that I took, okay, for del square T del x square plus del square T del y square equal to 0, I will get this value for every point. This will tell me that my hypothesis was not complex enough or complicated enough. So I can modify my hypothesis. So let me use a simpler function. Something like W0 e power x plus W1 e power y plus W2 e power xy, etc., etc. And let's say I take some W5 terms. So when I take T of xy is something of this sort, and I do d square t dx square or del square t del x square, this will give me W0 e power x plus, let's say in this case, W2y e power xy, so on and so forth. I will have an analytical expression. Now, once again, say I have only 5 or 6 unknowns, take 6 measurements. These measurements all say the same thing, del square t del x square plus del square t del y square equal to 0. So for example, I could get something like W0 e power x1 plus W1, I should have written W1, or W2 y1 e power x1 y1, so on and so forth, plus W5, let's say W5 was the term x square y square. Then if you differentiate it with respect to x, you'll have something like 2x plus some derivative due to y is equal to 0. Once you write this will again look like a matrix, except this will be a little bit more complicated. This will represent del square t del x square plus del square t del y square, all the coefficients like e power x1, y1 e power x1, y1, so on and so forth. And you will have W0, W1, W5 equal to, on the right hand side will be 0, 0, 0, 0, 0, 0. Okay. Once again, this can be solved. I'm explicitly avoiding boundary conditions, which I'll talk about later, can be solved using simple linear solutions. This gives us W0 through W5 is the same as before. Now notice what we have done here is we don't need this is completely physics informed. No need for T measurements. Now, why is there no need for T measurements? All we did is we have simply said that at each of these 6 points, the physics of the problem, which is del square T equal to 0, is imposed. And all we had was a hypothesis function. It could be quadratic like this. It turns out it's a bad function because nothing is left. You can now add cubic, quartic, power 4, sine, cos, whatever you have. Or we could also use neural networks. So if I use 6 measurements and the only number of parameters in my neural network are 6, you could solve it, except there is one difference. This is a linear system because my hypothesis was linear in W. Whereas a neural network is non-linear, as we have seen in the last 3-4 weeks in W. So instead of getting a linear system, we will get a non-linear system of equations to solve. Now, again, you can solve this using Gauss-Newton, or you can use Liebenberg-Marquardt, or you can use gradient descent. Now, the question is this: should we always have number of points equal to number of weights? So for example, Let's go back to the very first case that we took. We took 6 measurements here. 1, 2, 3, 4, 5, 6 at these 6 thermocouple locations, let's say. And we also had exactly 6 unknowns, W0 through W5. Is it required that the number of thermocouple measurements should be exactly the same as the number of unknowns? The answer is no, because we have been doing this throughout this course. What do we do? If, let us say, I have only this, but I have more points. Let's say I keep on adding more thermocouple measurements and I go till, let's say, 100 thermocouples. Now, what do? I don't have to increase the complexity of my function. All I need to do is, instead of solving this system of equations, I solve the equation in a least square sense. Why is that? Okay, so let's come back here. I'm going to revisit. I'll call this method 3, which is polynomial with more measurements, more data than unknowns. Where have we seen this before? In the slab problem. In the slab problem, we had 6 sensors, but our t hat was simply W0 plus W1x, only 2 unknowns. So instead of trying to satisfy every single thing, all I say is, okay, you have a prediction. This is the prediction. You try to minimize t minus t hat square at all these points, I equal to 1 to 6, 1 by 2 times number of points. Minimize j. So notice how this comes naturally. Let us say the number of points was only 2, like I made only 2 measurements. Then I'll have one exact value of W0 and W1. If I now make 3 measurements, it is not always certain that the same W0 and W1 will satisfy these 3. And all we do is, okay, instead of satisfying these 3, I will have something that goes in the middle. So let's say temperature like this. You have something of this sort. This will be my hypothesis function. So if I have more data than the number of unknowns, you simply do a least square. We can do the same thing with method 4. Method 4, suppose I have a neural network and I have 100 data points once again. 1, 2, 3 up to 100. And let's say number of weights in the neural network or in the hypothesis function I chose was, let us say, only 50. Then if it was exactly 50 and exactly 50 here, I would have, if data equal to weights, plus we have unique solution. In fact, this, as you know, is the nature of inverse problems. But if data is greater than weights, we have an imposed problem. And all we need to do is use least square. So instead of solving the nonlinear system of equations exactly, all you need to do is to minimize JPDE. JPDE simply says del square t del x square, whatever expression we get, plus del square t del y square. Instead of being 0, I will minimize the square of this summed over all the individual points. This is a very, very, very simple idea. Okay. So JPDE simply minimizes the sum of these squares over how many ever points this is. So this is 100. Then basically get optimal W's. Okay, I'll re-emphasize this point. Notice that if I had exactly 50 points, there is no optimal W. The thing that minimizes this will be such that at each point I can actually satisfy this exactly equal to 0. But the moment I increase the data points, you have a regularization effect. you add more and more points, you actually have multiple choices of W, which would have satisfied this. But what you want to do is to find that which minimizes del square T del X square plus del square T del Y square, the whole square. Okay. Now, this actually gives you a rubric for what we were doing in the neural network method. Whenever you get confused about using a neural network, you can think of a normal function. You can just think of T of xy or T of xyz is an actual function like W0 plus W1 sine x plus W2. It is some hypothesis function. It really doesn't matter what that function is. Once you give that, since we know that neural networks can approximate everything, rather than giving functions, handcrafted functions like this, we give a general neural network so that once we solve W0, W1, W2, we know it can approximate the function that we are looking for. Okay. Now, I hope that this made the idea behind pins a little bit clearer. In the next video, we will see how we can actually incorporate boundary conditions in two different ways. One is the one that was pioneered by Lagares, and the next is what was the modification by Risey. And we will see how the modification by Risey actually enables us to solve inverse problems very elegantly. So I'll see you in the next video. Thank you.